Hello everyone, thanks for stopping in, and today we're going to be looking at our last packet of notes for Math 120, and this is going to be our foray into the world of statistics. Now there's a healthy amount of pages here, but a lot of it is going to be definitions. So let's dive in, and a first definition when talking about statistics would probably be statistics, right? So statistics is the collection, study, analyzation, and conclusions formed by data. Is the collection, study, analyzation, and the conclusions formed by data. So statistics is all about data. You collect data, you study data, you analyze data, and you draw conclusions on that data, right? So what is data? Data is measurements, observations, or information relating to the subjects being studied. So data is measurements, observations, or information relating to the subjects being studied. Now, we also have two definitions that kind of go hand in hand, and that's population and sample. Population is the entire group of interest in a statistics study. It's the entire group of interest in a statistics study. The population is the whole group you want to study. However, many times it's unrealistic to collect data on the whole population. A good example, let's think about our country. There's 300 million people in our country. It's unreasonable for me to expect to ask all 300 million people or collect data on all 300 million people to get my conclusions, right? So in order to do that, I can collect what are called samples. Samples are subgroups taken from the population. Maybe I find 1,000 Americans I want to survey. My population is American citizens. There's 300 million of them. It's unrealistic for me to collect data on all of them. So I just collect data on 1,000 people. And then I use the statistical techniques from that smaller subgroup to make conclusions about my overall population. You're kind of getting a small snapshot of the group to then broaden your findings out to the overall population. So population is the overall group being studied, but samples are the smaller groups taken from the population. Now, there's different ways to take samples from a group. The first method, there's going to be 5 of them, right? There's going to be some on the next page as well. The first method is just regular old random sampling. And in random sampling, each member of the population is equally likely to be chosen. Each member of the population is equally likely to be chosen. It's random, right? A good example of that would be names from a hat. Let's say I wanted to collect data on our class. I could put everybody's name in a hat, right, and then draw 3 names out of the hat. That's totally random. Everyone's got an equal chance of being chosen, right? Another example besides names from a hat might be a random number generator. There are computer programs that are designed to give truly random numbers. And maybe you have a list of all the population, and you get 100 random numbers, and you survey those 100 people within that group, right? Random number generators are another common way we can randomly sample, right? And there's plenty of others. There's thousands of examples for each of these. We're just going to take a look at a couple. Systematic sampling. Systematic sampling is every kth. Here, k is some number. Maybe it's every 20th, every 5th, every 100th, every kth. I don't know what number, but every kth member of the population is sampled. An example might be calling every 10th number in the phone book. You go into the phone book and you call every 10th number. This is not random, is it? The first person will never be picked with this strategy because they are always going to be the first person. They're never going to be the 10th person, right? It's not random. There's a system, but it's not random. Calling every 10th number in the phone book. Maybe another example might be testing every 250th cell phone for defects. Maybe you work at a cell phone manufacturing plant and you need to do quality control. You need to make sure the cell phones are good. Maybe off the assembly line, there might be 1,000 cell phones, 2,000, 3,000, 10,000 cell phones made in a day, right? You can't test every single one for all possible defects. So you can take every 251 off the assembly line, right? The first 249 go in their boxes, then one goes to be tested. Then the next 249 go in their boxes, then the next one goes to be tested, right? Every 250th one gets tested. It's systematic. Every kth member is sampled. So that's systematic. Next is cluster. Cluster sampling involves splitting the population into groups. So first, you split the population into groups and choose some number of those groups. So you split the population group and you choose some number of the groups. Let's say you got 10 different groups. You pick 3 of the groups. You survey, you sample all members of those groups. All members of those groups. And an example might be city blocks is a good example of cluster. We're going to split our city. So let's draw a city, We'll just draw, here's our city. It's a nice grid-shaped pattern of streets. And I am going to ask everyone that lives on these blocks. I chose those 3 blocks. My clusters, my groups, are the individual blocks of my city, right? So I'd walk around this block and ask all the houses on that block. Or this block and all the houses on that block. This is a common way to collect data in cities. You do city blocks, right? Because you can't ask everybody, let's say you're in New York City, you can't ask all millions of people in New York City your sample questions, but it might be reasonable to go to a couple different blocks of the city and ask everyone on those blocks the questions you want to ask, right? Because you don't have to travel all over the place. Maybe you want to collect data on America, and you do the same thing, but instead of visiting city blocks, you just pick like 10 different towns to go visit and get your data in those 10 different towns, right? You sample all members of those groups. That's cluster sampling. Now, stratified sampling starts off the same. You split the population, I'm abbreviating it POP, into groups, but now you sample the same number of subjects from every group. So you split the population into groups, just like cluster. Stratified and cluster both involve splitting the population into groups. Cluster, you choose groups to sample. Stratified, you choose people from every group to sample. So an example might be split the population into male versus female. So maybe you're doing a medical test, and you're worried that there might be differences between male and female interactions. You know, medicines might interact differently. Male and females have different chromosomes. There's other differences between our bodies, right? Different levels of hormones. You might want to check the effects of your medicine on males versus females, right? And choose 50 of each. You choose 50 of each. So these two are similar because you're splitting them into groups, but how you deal with the groups is slightly different, right? Here, you pick a couple groups and ask everyone within those groups. Here, you ask the same number from every group. So if I was going to do the city blocks, but make it stratified instead of cluster, I could ask 10 people on each block. Every single block, not just these 3, the whole total blocks, right? These are similar, but different. And the last is convenience sampling, and this is use the easy to get data. And a great example is ask neighbors or friends. It's easy to ask your neighbors. Phone surveys are convenience. You ever watch the news and they put up the phone number and ask, call in with your opinion on this subject, and they're collecting data that way? That is a terrible way to collect data because it's easy for them to do it. They just put the phone number up and people elect to call in, but it's not good data collection because who's more likely to call in? The person that feels somewhere in the middle on an issue or someone who feels really strongly on an issue, right? Think about things you see on TV, like political issues, environmental issues, controversial topics of that nature. The people who are more likely to call in are the people who have strong opinions one way or another, not the people somewhere in the middle. Phone surveys are not good. Asking your neighbors is not a good way to get data. Now, these are 5 different ways to collect data. These aren't the only 5 sampling methods, but these are the only 5 we're going to look at. Now, let's take a look. Let's identify. We're going to be given a scenario and we want to identify which of those 5 it is. So these are multiple choice, right? Our options are random, systematic, cluster, stratified, or convenience. The first is every 20th soup can coming off an assembly line is checked for defects. Well, that's systematic. The 20th part told me it was systematic. That's systematic sampling, right? Let's see. A $50 gift certificate is given away at the annual mathematics convention. Tickets are placed in a bin and then mixed up. The winning ticket is then selected by a blindfolded person. Well, that sounds random, right? Everybody's ticket is equally likely to be chosen, right? It's random. Let's see. Children in a large city are classified based on the neighborhood school they attend. So right away I'm splitting things into groups based on school. A random sample of 5 schools is selected. All the children from each selected school are included in the sample. So here I split into groups, the schools. I chose some of the schools and I sampled those schools. That is cluster. Be careful. The word random shows up here, but the overall selection method was not random. Because if you don't attend one of those 5 schools, you're not as likely to be chosen. The schools might be different sizes, right? There's not true randomness. The schools might have been chosen randomly, but the children were not chosen randomly, right? The children are the ones being sampled. The children are sampled, not the schools. The schools are the groups. Be careful. So that's cluster. How about on the next page? We got the first 50 people entering a zoo are asked if they support an increase in taxes to support a zoo expansion. Well, that's just convenience, right? That's convenience. The first 50 people to show up are asked about their opinion. That's just easy to do, right? You just put someone at the gate at the opening of the zoo and you ask them. This is bad data collection because who's arriving early to the zoo? Who's the first people to arrive to the zoo? People that really want to go to the zoo, right? Are they more likely to support increases in taxes for a zoo expansion? Yeah. Might that be a good idea? Maybe, depending on how you feel about zoos and taxes. But it's not good data collection. You shouldn't use this data to draw conclusions on this issue. It's just convenience. It was convenient for them. And then, all registered vehicles in California are classified according to type: subcompact, compact, midsize, full-size, SUV, and truck. A random sample of vehicles from each category is then selected. So I'm taking vehicles from each category. That is stratified, right? I'm taking things from each category. And so these questions are multiple choice. You're identifying which sampling method you used. Now, unfortunately, one of the major issues with statistics is it is wildly misused. And that is one of the things I want us to be most aware of, are what some of the misuses might be. What can we be aware of? How can we avoid misusing statistics? And the first is being aware of sampling issues. Bad samples lead to bad data. If your sample is not random, your data is bad. Almost always. Random samples are the best, because then all opinions and all data points are equally likely to be chosen. It's random. They're equally likely to be chosen. So bad samples lead to bad data. Random is best. Random is best. Random is best. So, sampling issues, bad samples lead to bad data, random is best. What other sampling issues might we have? And another one might be non-response of subjects. And I always think back to when I was a high school student, we had a DARE officer come into our school and give us a survey about marijuana use. Is that a good way to get people to truthfully answer the questions? No. There's students who are likely to non-response or even lie in those responses, right? Non-responsive subjects. That's a sampling issue. The person administering the questions should be an impartial observer, just collecting the data, right? A DARE officer automatically implies a certain bias in responses, right? How likely is someone to be honest about drug use to someone whose job is to, punish drug use, right? So non-response or straight up lying are issues with subjects. So those are all issues that can come from our samples, right? The last issue is the sample does not represent the population. Sample not representative. For example, I want to collect data on Americans, and I ask 1,000 people in Saranac Lake about some questions. Is that representative of America? No, it's representative of Saranac Lake. If I ask, 1,000 New Yorkers, that's still not representative of America. That's representative of New York. Your sample needs to represent your population. Everyone in the population should be able to be chosen for your sample. So that's some sampling issues. Next is misrepresentation of data or information. Misrepresentative data or information. So here, we might have misleading conclusions. And I always think of this as the pop culture, sort of articles. Like when you're reading, maybe a BuzzFeed or something, and they talk about a scientific study, but you're kind of finding it hard to believe. They might be misinterpreting or using a misleading conclusion. The data might imply something, but they're misleading you with the conclusion. Misrepresentation data. Another one might be bias in the publisher. For example, let's say you find a study that tells you all the health benefits of eating cheese. It's all about how great cheese is. And you're like, huh, I like cheese. That seems reasonable. Like, cheese can be healthy. But then you look at who put the study forward, and it's the Dairy Farmers of America brought the study forward. There could be bias in the publisher. Dairy Farmers of America have a potential to gain from a certain outcome for that study, right? They have, bias. So misleading conclusions, bias in the publisher. You could also have an issue with the data collected does not correlate with the conclusions being made. Sometimes your data collected might be good data, and the math you do might be good math, but it might not correlate with what you're actually trying to determine. And this is sort of like you're doing all the right work, but for the wrong reasons. So your data collected does not correlate with the conclusions being made. An example of that might be I get everybody's test scores on the final exam, and I also get everybody's height. And I noticed that taller students did better on the test. So therefore, the taller you are, the better you are at math. That doesn't necessarily correlate, right? That is not a good conclusion. I would need to study that. If I want to talk about height and math scores, I would need to find a way to do an experiment relating those two variables. I can't just measure the two things and then assume they relate. That doesn't work. It doesn't work that way, right? I have to know they're related before I can study their relation. So just be aware that data can be misused, right? And information can be misrepresentative, right? The last one for misleading or misuses is misleading graphs. And there's going to be two types we want to look at. The first type here is pictographs. Pictographs. Here's where you use a picture to represent the data. So here, a two-dimensional picture, a 2D picture, is used to represent one-dimensional data. And an example of this might be something like this. And we're talking, this is men's salary, and this is women's salary. And we're talking about the wage gap. Now, unfortunately, this is a very real issue facing our society. Many times, for the same work, men and women make different amounts of money. Typically, men get favored with higher salaries for the same work than women. There's also racial biases in that same category, right? Unfortunately, that is a reality we sometimes face in our world, right? That is a true measurable fact, that there are wage gaps, right? An unfortunate truth. However, this graph is misleading us. Money is a one-dimensional data. It goes up or down, right? It increases or decreases. It can't go left or right. A picture is two-dimensional, right? It has an up and down and a left and right. Using these pictures to represent, scaling the top down, like if the data here is saying that a woman makes 75 cents per dollar a man makes for the same work, I scaled the edge down to be 75%. The area here does not represent the actual numbers. The picture is misleading us. the information is true, right? The wage gap is a real problem, but the pictures themselves are misleading us, unfortunately. And we see this all the time. If you turn on a news channel, they might be using pictures of houses to talk about populations. Populations are one-dimensional. They increase or decrease. A picture of a house is two-dimensional. Things like this are misleading. In general, you should avoid using pictures in statistics, because that's not good data. It's just a picture, right? It's just a picture graph. You should just let the data do the talking. Don't let the pictures do the talking. The next one is non-zero vertical axis. And for this, we always start a vertical, I'll abbreviate it vert, axis at 0. An example here might be, I'm going to draw two of the same graph. And we're going to put choice A and choice B, and choice A and choice B. On this one, I'm going to do 1, 2, 3, 4 dashes, 10, 20, 30, and 40. And this is the percent that chose A or B. A is going to be up here at about 40. B is going to be up here at about 30, just a little above 30. B is just a little, so maybe like 38 and 32, right? Doesn't matter. You're just drawing them close, with A being a little bit taller. Now here, I'm going to start at 30, and up here is going to be 40. Now A, that went pretty close to 40, and B went a little bit above 30. These two graphs technically tell me the same information, that A is just a little bit above B. But at a quick glance, in this one, they look close, which they are. In this one, it looks like A did twice as good. And I promise you, if you watched the news during the election, that you saw graphs like this, where, you know, Trump-Biden or Biden-Trump, right, where the graph was misleading. I see these all the time in news outlets. They use non-zero vertical axes to make the difference look exaggerated. You should always count a regular scale on your graph. Always start at 0 and count up by a reasonable scale. Here we just jumped to 30 and went up to 40, right? This isn't a good scale. That's only for vertical axes. The horizontal you can scale however you want, because you know, if you think we don't really care about independent and dependent variables at this point. That's a little beyond where we're talking, but always be careful with your non-zero vertical axes. This graph is better. Yes, no. Graph like this, not like this. And I guarantee you'll see one of these in your life, probably in the near future if you're looking for it. We see them all the time in the news. So that's some misuses of statistics. Now what about some calculations? On the next page we've got some calculations. So we're going to have a few different definitions here. You know, it's a healthy page full of definitions. The first is going to be an average. In statistics, an average is any value that is used to describe the, and I'm going to put quotation marks around it, center of the data. And the reason I put quotation marks is because the word center can be misleading. If I think about this paper, this point right here is the center of the paper, if I only consider the top edge. This point over here is the center of the paper, if I only consider the left edge. This point right here is the center of the paper, if I consider the whole paper as an area. Right? There's different ways to think about the center of an object, just like there's different ways to think about the center of a data. Now, the four we're going to look at are the mean, the median, the mode, and the mid-range. Now, the mean is probably what you normally think of when you hear the word average. The mean is the value found by summing, adding all data, right? You're summing it, all the data, and dividing by the size. The mean, right? By the size. You add them all up and you divide by how many there were. The formula, the mean, is equal to, well, the mean is equal to the sum of data divided by the number of data values. We use two different symbols for the mean. We use x bar, x with a bar over it, for a sample mean, and we use mu for a population mean. We use two different symbols when we talk about the mean. One for sample, one for population. We use an x with a line over it for sample, and we use this weird looking u. It's called mu. It's a Greek letter. It looks kind of like a U, but it's called mu. The way I draw it, I go like up, and then I draw a U. That's called mu. You can also sometimes just write the word mean, right? Just these symbols pop up. So that's the mean. The median is the number in the center, is the value in the middle of the ordered list of data. So you put the data in order and you find which number's in the middle. That's the median. The mode is the value that appears most frequently. The mode is the value that appears most frequently. Which one shows up the most? Bimodal means two of them are tied for the most. Means there's two modes. That's what bimodal means, right? There's two modes, both of which are tied for most frequent value. Most frequent value. And then no mode means no value was repeated. If no value is repeated, there's no mode, right? Nothing can appear most frequently if everything's tied as it showed up once. You could also have trimodal for 3, quadmodal, multimodal. We don't really say tri or quadmodal. We usually say mode, bimodal, and then if there's 3 or more, like let's say you have 3 things that are tied for the most, usually you just say multimodal. If there's 4, multimodal. If for some crazy reason there was 20 of them that are tied together, you would say multimodal also. So that's the mode. And the last one is the mid-range. The mid-range is the value halfway between the maximum and minimum values. Is the value halfway between the max and the min. The formula for mid-range is mid-range equals the max plus the min divided by 2. You add the maximum value to the minimum value and you divide it by 2. What number is halfway in between them, right? And these 4 concepts, the mean, we say arithmetic mean to be specific, because there's also geometric means, geodesic means. We only care about arithmetic mean. I'll just say mean. I know we mean arithmetic mean, but it's technically the arithmetic mean. But mean, median, mode, and mid-range. You've probably seen mean, median, and mode before in your life. Most people have encountered these values or these ideas before. Mid-range might be new, but mean, median, and mode are usually pretty standard. Let's take a look. Let's figure out what's going on. The salaries of 8 social workers in thousands of dollars are listed below. For the set of data, find the mean, median, mode, and mid-range. I'm going to do the mode first. Mode's the easiest. Let's see. 40, 25, 28, 35, 42, 60, 60, and 73. 60 is the only number that was repeated. So 60 is my mode. My mode is 60. Now, let's do the mid-range next. The mid-range. We'll do the mid-range next. We're going to do some scratch work over here. What's the biggest number here? 73, right? We take our max, and we need to add our minimum. What's the smallest number? Is 25. And we'll divide by 2. Well, 73 plus 25 is 98, right? Right? 73 plus 25 is 98. So we get 98 over 2, which is 49. So the mid-range is 49. Next, I'm going to do the median. Why not? Let's go to the median next. The first thing for the median I have to do is I need to order my numbers in order. Well, 25 is the smallest, then 28, then it looks like 35, then 40, then 42, then 60, then 60 again, then 72. Right? And then I double check. There's supposed to be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. I've got all of them. Now, what I'm going to do is I'm going to cross off the endpoints. And then I'm going to do it again. Then I'm going to do it again. I'm looking for a number in the middle. Now, when I get here, I've only got 2 numbers left. What number's in the middle? Both of them are in the middle, right? I have 8 numbers. When you have 8 things, there's not going to be something smack dab in the middle. There's going to be 2 things smack dab in the middle. It's an even number, right? There's not going to be an odd one out left over. So I need to find what number is halfway between 40 and 42. Well, between those would be 41, right? Now, if you had 9 numbers, you would have 1 left over when you crossed off from the end. Anytime you have an odd number, your answer will just show up. Anytime you have an even amount, you have to look at the 2 middle ones. That's the difference between even and odds when we're looking at the median. And now, lastly, we'll do the mode. For the mode, we add all of these numbers up. The mean. The mean. When we do the mean, we add all the numbers up and divide by how many there were. Well, there's 8 of them, so I just have to add them all up. Let's see. 40 plus 25 plus 28 plus 35 plus 42 plus 60 plus 60 plus 73 gives me 363. Divided by 8 is 45.375. 45.375. Now, these 4 numbers are my measures of center. Each of these numbers has a use. But which measure of center is the best? Which measure of center is the best? They're all different, right? I got different numbers. Which one's the best? Well, the mean and median are the 2 strongest values. The mean and median are the most useful. Which one of those 2 is better? It varies. It varies which of the 2 is better. And what causes it to vary? It depends on the data set you're working with. In general, we like means in statistics. However, sometimes the mean might not be a good representative measure, in which case the median might be better. The mean is usually better, but sometimes the median is better as well. Usually it's the mean, though. Almost always it's the mean, sometimes the median, though. So just be aware those are the 2 most useful. So those are my measures of central tendency. Mean, median, mode, and mid-range. They're fairly quick to calculate, right? You just gotta, mid-range, you just plug in max, min, divide by 2. Median, you just find which number's right in the middle. Mean, you add them all up and divide by how many there are. Mode, you find which one shows up the most, right? And those are the measures we will use. And that brings us to the end of our introduction to statistics. I wanted to take a moment to thank all of you for a lovely semester. I know this probably wasn't the most normal semester for you, or myself, but I'm glad we're able to work through this remote learning. I hope you found it agreeable and enjoyed the class. I thank you all for being a part of the class, and I hope you best of luck on your finals, and I'll see you in live sessions as we wind down the end of the semester. Thanks for stopping in, and I'll see you next time.